introduce you to Sarah Elmore, who's going to teach you how to make a star on Earth. Over to you, Sarah.
Okay, so I'm going to tell you a bit about the work that we did and the lab that I work at in Oxfordshire. So what we've done is we've made our very own star on Earth. First, I'm going to tell you a bit about why we're doing this. So this is a picture of the Earth taken at night by satellite. You can see all the main cities in the developed countries are quite bright. Now, if we go to what we think this is going to look like in 2050, gets a lot brighter. So this is partly because all the developing countries are going to try and get up to the levels that we are now, and also the population is going to grow. So we're going to use a lot more energy. So as I say, population is going to grow quite dramatically in the years to come, and whatever model we use to predict our energy usage over that time, even the most moderate one, we're going to need a lot more energy from somewhere. So currently we use fossil fuels, that's what we use to get all our electricity and power at the moment, which has been fine, but these were formed over millions of years, and we're using them far too fast for that. And on top of that, as a lot of people know, there's the CO2 emission problem with these fossil fuels, which is contributing to global warming, which is why we're having these issues now. So what we think is the fusion energy that happens inside the sun and all stars could help solve this problem if we could only harness it on Earth. So what's fusion energy? So what we have is two light nuclei, which is the middle of an atom, forced together to produce a larger nucleus and a neutron. Now what happens is this bigger nucleus is not as heavy as the two that formed it in the first place, and this extra mass that is lost gets converted into energy using Einstein's famous formula, and it's this energy that we want to try and use. So what do we need to do? How are we going to do this? So as you know, the sun is really hot. So all sun and stars, they're hundreds, tens, millions of degrees C. But when we get to this stage, we're actually in a form of matter called a plasma. So for anyone that doesn't know that, I'll just run through the states of matter that you will be familiar with, and then I'll explain the difference between that and a plasma. So we start with a solid state. All the objects we've got nice lattice of atoms, everything's nice and compact and regular. And you've got your electrons spinning around your nucleus in your little atom forms. Now moving to liquid, still got atoms, they're moving around a bit more, but they're still held together, just like water. Now, if we heat that even more like boiling a kettle, we get a gas, like steam, and it's going a bit more crazy, and it will expand to fill whatever space you've got, but they're still in their formed atoms. Now, if we get to even higher temperatures, which is when we form a plasma, one second, I'm having technical issues with my plasma. There we go. So at these higher temperatures, we no longer have our atoms. Instead of the electrons spinning around those nucleuses in the form of atoms, they've stripped off, and we've basically got a superparticles, half of which are going to be the electrons that are negatively charged spinning around, and then the centre that was left will be positively charged, which are what we call ions. So this is what we need to get. Now, in order to get these things to fuse, as I just said, they're now charged particles because they're no longer neutral atoms because the electron's separate to the centre. Now, when we want to do that, as you know, just like with magnets, if they're the same charge, they don't want to go together. So what we have is, we've got these particles, try and push them together, they don't want to fuse. So what happens is we need to come over what's known as the Coulomb barrier, so that when they're close enough, they will fuse together. So what we need to do is heat them up. So if we heat them up so they're going faster, so they get close enough to other particles, this happens. And that's when we get fusion. So we have to make sure they're hot enough that we can actually get them to interact with each other, and then we can get the energy out. Now, just like a gas fills everything it can get in, the plasma's just the same. You see these particles, they're highly energetic, they're going all over the place. We need to bottle this somehow. It's all right for the sun. The sun is so big that gravity holds it together on its own. Now, obviously, we can't make a star as big as the sun on Earth because it would envelope us if we could even do that. So instead, we need to form a bottle, and what we use is magnetic fields. So because these particles have a charge, if we send a directed magnetic field in one direction, these particles will orbit around those magnetic fields and they'll travel along them. So we'll be having electrons going one way and ions going the other way because of their different charges. Now, still we've got a problem, because if we make a tube like this, it's still all going to shoot out the end. We're going to have one end that's electrons, one end that's ions. So what we've done in the design that we use for all our machines is called a tokamak. And basically, you bend this round and you form a torus, or as I like to call it, a donut design. This is the way that most people can understand what shape I mean. And then instead,
we've got the particles whizzing round and round and we don't lose them. And this is the design that we use for all the machines that we make as experiments to study how we can get the fusion energy out. Now, I'm now going to show you our machine, and this is a plasma inside it. Before I start it, just to put this into context, this video is taken with high-speed imaging, so it's a lot slower in real life than this video will be. So our device works as a pulse, so because we have to put all this energy in, it's actually only half a second, so this is a lot slowed down. So just to put that into context for you. So this is basically how we start up the plasma. For us, it's quite a small device because when we move to power stations, they're going to need to be a lot bigger, but it's still 4 meters high, which is quite big next to me. So what we first do is we fuel it by putting gas in the middle. So this bright spot here is where the gas comes in. And then we need to ionize this and form it into a plasma. And then once it's charged, we can accelerate it, and then it will turn into a nice hot plasma. And we use our magnetic fields to form this shape. And then basically our particles are moving around. So this is the area. It's basically, this is slightly more of an apple, a chord apple shape, because it's a compact design that we're working on at the lab that I'm at, and this is the UK's device. So what you'll see is the bright bits. The reason you can see straight through the middle of it is just because it's so hot. But every now and again you'll see these flashes. They're the equivalent of what happens when the sun kicks out a solar flare. So the same thing happens with us because it gets so hot in there, it wants to throw out the energy. I'll come back to them because they're a small problem for us later. But basically what we need to do is we use the magnetic fields to hold it together, but because the magnetic fields go all the way out to our material, and that's going to be far too hot, because remember this is sun temperature and these are just normal metals and materials, we use another magnetic field to take this channel of heat down to a piece of material that is designed to take the heat, but at the same time we need to keep this hot, but this is a lot cooler, and this is basically where my work comes in. So this is the issue we've got. We want the heat because the heat is the energy and that's how we're going to power everything. But at the same time, to get fusion to happen, the red bit, that's going to be greater than the temperature in the middle of the sun. So that's going to be greater than 10 million degrees C. That's pretty hot. But where we're actually going to be having the plasma touching materials, it's got to be a lot colder than that because this is the materials that we've got. The materials we use in most of these machines are carbon. That's the same stuff that's in your pencil leads. So it's not going to cope with the temperature of the sun. You put that in the sun, that's never going to survive. So what we need to do, and a lot of our research is involved in trying to reduce the temperature as you get to these materials without reducing the temperature in the middle. So it's going to get an even bigger problem when we move this to bigger machines. So we need bigger machines when we actually want to take this power to the grid. So what we've got is something that's a lot more manageable so that we can understand it and do experiments on it. But at the end of the day, the biggest challenge is the middle's got to be really hot, otherwise it won't fuse. But the materials can't be, otherwise they'll melt, and then we've lost our bottle. So we've got to find a way to reduce the heat on the way to the material. So just to put this in context, this is where we are with our experimental reactor. So the heat that comes out of the kettle, not much of a problem, we can handle that. That's why we can all boil kettles. So we're more sort of the kind of power that we're dealing with when you're trying to cool down a car engine. Now, when we go to bigger machines, they're going to be much, much hotter. And this is the limit we've got on material now. The only thing that you'll really come across that uses bigger heat than this on, in normal daily, well, maybe not everyone's daily activities, but it's something like welding. But as you see here, when you're welding, all this material's coming off because you're actually melting it. Now, if we do that in our machine, that's like the worst thing that we can do, because if we melt these materials, we're going to have to keep replacing them. That's going to make a very expensive power station. But on top of that, if all of this can get inside of here, it's going to dilute the bit we care about, and we won't be getting the same fusion that was what we're doing this for. So we've got to find a way to, we can't change this unfortunately, because however much work the very clever people do in material science, we just cannot make something that's going to cope with this. So we've got to find a way to cool it down instead. So how do we do this? This is basically the kind of work we do in our research. So one idea is to spread the heat over a larger area, so that instead of it causing damage on a very small space, we have the same heat but we spread it. Then another idea is to try and cool it before it reaches the actual materials. But then the other thing that we have to think about, if you remember those bursts from the video that are like solar flares, these are even hotter than with the heat that we normally get. So we have to do something about them as well. So if we want to spread the heat, even if that channel that we've made with our magnetic fields to channel the heat down to material stays the same width, if we just go to a bigger radius, just the sure fact that the area will increase with the radius squared because it's a circle, we can spread it over a larger area. And you might just think, right, simple, done, job done. Only problem with this is that this will only work if you make it bigger. But in making it bigger, you need magnetic fields, otherwise you can't control it anymore. And they're quite expensive. You don't want to be making a massive machine that you've got to pay for the magnetic fields for, because it's going to make very expensive electricity. If you want to try and just say, we'll make the whole thing bigger, you don't solve a problem at all, because as soon as you make the plasma that's doing the fusion bigger, that's hotter, and then you don't gain anything. This is something we are doing though. So at the moment, our machine that I've been working on, it's having an upgrade, and this is one of the things we're trying, but it doesn't work on its own. So our other idea is to try and cool it on its way down. So, as I said, we channel this heat down these edges so that till they touch these materials. Now, if we can extend that, just like anything that conducts, if you have something cold here and something hotter here, you'll get a change in temperature along that. And so if we make this longer, this hot here is going to cool down more before it gets to the end. So that's one way of doing it. The other way of doing it is, because our particles are charged, that's why they're following the route that we've given it. If we put something in that's just gas, then we can fill this area with gas. The gas will not follow the channel and it won't go down to the material surface. So instead, if these collide with our very hot particles, they can take some of the energy, and then instead of taking it straight to the surface, it gets shared in this area. The only problem is you don't want these cold particles getting up into the bit where we're trying to make fusion happen. So you have to try and contain this down. And again, this is something that we're looking at doing in our machine. So we're taking both the ideas of taking this to a larger radius so the area is bigger, also extending this and filling it with gas, in the hope that that will get us to a stage we can have a really lovely hot plasma in the middle, but not cause damage to our materials. Now, hopefully that will all work, but the thing we still got to think about is these. So, as I'm sure some of you are familiar with, this is what a solar flare looks like. This is exactly what I showed you before in the video, that we have these bursts, and these are basically the same thing as solar flares. And as you can see, the material comes out at the edges, and if that's going to touch material, that's going to melt in, that's going to cause damage. So before we can get to a stage where everything's solved, this is the other thing we need to deal with. And there's lots of ways that people are trying to do this, but it's quite complicated and involved physics to do with it. But it's something that if anyone's interested in, please do look into it. But the aim of what we're trying to do is solve all those problems so that we can have a very lovely, stable plasma that's working really efficiently in the middle, and then we'll use it in the same way that we burn fossil fuels now to try and get electricity onto the grid. So this is what we're all working towards. So I hope you found this interesting, and I hope I've inspired some of you to look into careers in this. If you're interested in more information, there's a website, Facebook and Twitter, and also any of you that really want to come and have a look, we do have open days and we do school tours, so talk to your teachers if you want to go and have a look. Thank you very much.
A quick 5-minute Q&A if anyone's got any questions. If not, feel free to grab Sarah around the room, around the building, if that's all right.
Yeah, I'll be around.
Collie you and ask questions at you. If not, stick around for the next talk or have a wander around. Thank you for coming.
Thank you.
Thank you. I've got to try and get out of all this now.
Good.
Yeah, I think so. I don't know. I've got to do it again.